In this video, I'll walk through an example using the ideal gas equation. Let's get right to it. The ideal gas equation is PV equals nRT. So pressure times volume equals N, number of moles of the gas, times R times T. R is a constant, where R equals 0.0820057, and there are some units on this. Liters times atmosphere per degrees Kelvin times mole. So what this is telling us is that this R in particular requires that the pressure be in atmospheres. So I'll write that pressure has got to be in atmospheres. And the volume has to be expressed in terms of liters. So the volume in liters. And the reason I'm specifying this is because there are other constants that you can use for R, or other values for R, but that would change the labels here, and therefore that's why the constant would be different if you used different labels there. And this is found by using a gas at a STP, or standard temperature and pressure. Okay, K is Kelvin, so K, or Kelvin, and that simply equals degrees Celsius plus 273 degrees. It turns out that negative 273 degrees Celsius is absolute zero, and Kelvin is a measure of 0 Kelvin is absolute zero. Mole, N, so that is N equals the number of moles of the gas. I should say, the number of moles of the molecules of gas. Okay, so let's see what the problem is. Dry ice is solid carbon dioxide. That is true. When you buy dry ice, it's just carbon dioxide in its solid state. A 0.370 gram sample of dry ice is placed in an evacuated 2-liter vessel at 25 degrees Celsius. Evacuated, meaning it's empty and it doesn't have any air already in it. But it's a 2-liter vessel. That's the possible volume of this vessel. Calculate the pressure inside the vessel after all the dry ice has been converted to the CO2 gas, the carbon dioxide gas. So we'll start with the PV equals nRT. And this problem is giving us some stuff. We have the volume, that's the 2 liters, and we have the temperature. We can just add 273 to that to get our Kelvin. What else do we have? We have the number of moles, but not directly. We are given 0.37 grams, and we're going to have to convert that to the number of moles. So we have the volume, we have the number of moles, we have we'll find the number of moles, we have the temperature, and R is this constant. And then we'll solve for pressure, because that's what it's asking for. So let's start plugging some stuff in. First, we have to convert 0.370 grams into number of moles. 0.370 grams of the carbon dioxide, multiplying by the correct fraction or conversion. We want to cancel out grams, so I'm going to put grams in the denominator. And the molecular mass of CO2 is 44.01, so 44.01 grams for every 1 mole of the CO2 gas. Grams cancels out, and it turns out that we have approximately 0.00840,718 moles of the CO2. And that's what we're going to use here for N. Okay, and I've held on to all the decimal places. Of course, don't round until the end. So start plugging in here. We've got P equals volume. We're in liters. So it's just giving us this volume in liters, so we'll just keep that. Pressure times the volume, P times 2, equals the N, and that is 0.008407118 is the number of moles, multiplied by the R, and that's 0.082057. That's the constant that we'll use, and then multiplied by the temperature. That's the temperature in Celsius, 25, plus 273. So for a temperature in Kelvin. And I've just kind of put that line in the next, continued that line right down here. All right, solving this equation for pressure then, pressure equals 0.103. Now I know we technically only have two significant digits here because, or one significant digit here because of just the one digit, 2 liters, but I'm gonna give you 3 significant digits just so we're not bothered by worrying if where it was rounded there. So 0.103 atmospheres is our pressure, 0.103 atmospheres. So that is about 1/10 of the pressure that you feel at sea level. 1/10 of the pressure. So pretty minimal pressure. And pressure is measured in, you could say, pounds per square inch, 14.7 pounds per square inch, or most of the time in chemistry, it's measured in millimeters mercury. So 1/10 of that, 760 millimeters mercury is the pressure at sea level. So 0.103 multiplied by that would be about 78 millimeters mercury, just in case you were wondering where that measured up, where that pressure was in millimeters mercury. So there is a nice example of the ideal gas equation. If you found this video helpful, consider liking it or sharing it with a friend.